if you use EDR.
In terms of the other contaminants?
Correct.
Yes.
So
That's a very good point. In fact, you know, one of the that is one of the issues associated with EDR is that it's more targeted towards particular contaminants. And so if those are your issues, and those are your only issues, it may be an appropriate and viable treatment strategy. However, if you have other things that commonly co-occur with nitrate, whether it be pesticides or other inorganic contaminants, then you start looking at other treatment processes that may have the ability to remove multiple contaminants via one treatment approach. Particularly at small system scales, you don't really want to be stacking up unit processes one after another, but to be honest, there are a lot of water quality cases where you can't avoid that, and oftentimes it's in these small communities where that's most prevalent.
Thank you.
Yep, thank you.
Next up, we have Rob Busby from our Central Valley Regional Board staff discussing disposal options.
Good morning, almost afternoon. Rob Busby, a supervising engineering geologist with the Central Valley Regional Water Quality Control Board. And my presentation is going to focus on the disposal options, not the treatment technologies. Chad just provided a good overview of the treatment technologies, which I think is helpful. And again, so I'll just focus on the technologies. So this was Chad's family tree, and so I'm not going to go over this because he just did that. I think I would like to add one thing about what we're seeing a lot, at least in the Central Valley, is, and he might have touched on this, was replacing shallow wells with deeper supply wells. So we're seeing that quite a bit more often. The rest of this he's already gone over, so for the sake of time, I'll move on. There are at least 33 facilities in California. Most of them are located in the Santa Ana region, and I think you'll hear about the infamous Santa Ana brine line, previously referred to as the Santa Ana Regional Interceptor. And as Chad, I think, was just discussing, a majority of treatment facilities options are ion exchange. But of course, they all produce a concentrated residual of varying degrees, shapes, fashions, and forms. Of course, so what I'm going to talk about is the various disposal methods for getting rid of appropriately those residuals. This is kind of a simplistic depiction of what we have here, but in essence, we have the well water, which is the most of what we're dealing with here. And of course, as we've all heard from UC Davis and everywhere else, and from our experience with the water board, the well water can be quite variable. You can have TDS issues or nitrate issues or both. You can also have VOCs. There could be other things going on. So that's an input into this treatment system. And then there's, of course, treatment chemicals, whether it's just simply dechlorination or whether there's other associated with activities that Chad just discussed. There's other potential chemicals. And then the end result, of course, is the good water that hopefully they can drink. And then the treatment residuals, which we need to either reuse or dispose of appropriately. And the characteristics of the residuals, it could be a lot of things, but the classic examples would be nitrates and salts, cations and anionic salts, a vast variety of metals, some benign, some are more of a threat, arsenic, as we've heard a lot about, and then there's just the actual biomass itself. All of these need to be disposed of appropriately. So what I like to call this slide is kind of the potpourri of options. Some options will work quite well for certain locations. Others, it's not going to be appropriate. Don't even think about it. But again, this is an overview of the potpourri of options. And basically, I'll go through each of these in following slides, but I wanted to give you kind of a template of what we're going to be talking about. The obvious one people have heard about is discharge with public sewer system. Okay, there's requirements with that, which we'll go into. Then there's the brine line, if there is a brine line, that there is in Santa Ana. Maybe there will be more in the future, who knows. There's evaporation, which is also part of the Title 27. You can have Class 2 surface impoundments, where you can concentrate the salts into a solid form in a permitted environment with the liner. So you're reducing your volume reduction by evaporating out a lot of that, and you have less residual to deal with, depending on to what degree you're doing that. Then there's the possibility, depending on where you are and the costs and everything else, of deep well injection. I don't hear too much about that now, but other industries for different reasons. There's deep well injection. Sometimes it's cost effective, sometimes it's not, and there's pros and cons with that. And then percolation, it's regulated percolation, where we have different programs through the water board, what we call the non-15 program. But waste discharge to land, if they meet certain criteria, that's another option, which I'll go into. And then there's advanced treatment for reuse, which I'm not an expert on. Others will talk about that. That's not really a disposal option, but it reduces the amount that you need to dispose of. So in terms of discharge for public sewer system, it should be noted that water quality characteristics of the waste brine can affect the feasibility and cost of disposal options. Proximity and access to coastal waters can be a significant factor in determining the burden of brine and cost of brine disposal. Generally, disposal is of greatest concern, again, to inland communities, which I think you just heard a little bit about. Discharge of concentrated brine to a sewer system is regulated either by POTW pretreatment program permit that will include concentration limits and other conditions and requirements, or the waste can be hauled to the headworks or to a landfill. Either way, the POTW receiving the discharge is regulated by the regional water board, us. The regional board can issue an MPDS permit or WDR orders for waste discharge to land. The permit or order will include discharge limits or concentration limits for TDS and nitrate and other constituents of concern, which can vary greatly from only a few to a long list. So that was the first one. And then, of course, there's a discharge to the brine line, which we don't have in the Central Valley region, but you've heard about Santa Ana. So ocean discharge of brine through a dedicated conveyance system like the brine line probably has the least impact compared to other disposal options. The devil's in the details, of course. In the Santa Ana region, virtually all brine waste is discharged to the Inland Empire Brine Line, previously referred to as the Santa Ana Regional Interceptor. The brine line is a pipeline that was constructed to protect the Santa Ana River watershed from salt concentrate and various saline wastes. Organizations who processes create a high saline waste that does not qualify for reuse, for use, reclamation, or return to the region, but does qualify ocean discharge. If they meet those criteria, they can use the brine line to transport the waste. The brine line pipeline carries the waste directly to the specially equipped treatment plant operated by the Orange County Sanitation District. After treatment, the waste is discharged to the Pacific Ocean. And then, of course, permits are required for this option, including concentration limits and flow limits and the like. Another one, maybe this is a little misleading, we say evaporation, but we discharge to a surface impoundment in Title 27, which is a waste to like landfills. In this case, it's a surface impoundment. So it's specifically designed to contain this wastewater, and it's usually either they're double-lined or single-lined, depending on the requirements of the facility. They're a regulated facility, usually at a landfill, but you can have them at other facilities that are closer to the source of generation, so you have less hauling costs and the like. And like I said, they require lining to protect groundwater. So they're very well-maintained, and they're regulated facilities. And then this kind of relates to the evaporation. As the water evaporates, your brine increases in concentration, and at some point, you can remove that salty, pretty much solid waste, and either dispose of it to a lined, permitted landfill, or maybe there's other reuse options depending on what the salts are. And then there's, of course, brine evaporators. I don't hear about those too often, but I'm sure that's another possibility. Again, it fulfills the same kind of end goal of reducing the volume and mass of the waste. And usually I think that's by getting rid of the liquid component of that. And typically I would think most of these wastes that are generated, the nearly solid brine waste at the end of that process is usually a non-hazardous solid waste, so it doesn't have to go off to some hazardous waste facility. But there's still a cost associated with that. Another one we don't hear about in terms of saltwater or disposal or brine disposal is deep well injection. I don't need to go into the details of that, but basically it's regulated by the US EPA. There's different types of classes. This would be a class 1 non-hazardous injection. For cost's sake, it would be constructed at the site of waste generation, because if there's a large volume, maybe there's options for when people transporting their waste to that locale. But that is an option. Again, it reduces there's the tank and haul issues. Again, it depends on your location, which is, maybe that's more of something that inland areas would might think about a little bit more, because the brine line might be a little more challenging. But then there's the cost. They're very deep. As you go down deeper, there's saltwater intrusion. The closer you get to the ocean, of course, the shallower it is to saltwater, and the farther you go inland, the deeper it is. So that's a factor. But depending on the circumstances, you have to go down quite a significant depth, and then there's costs associated with that, but nothing's free in any of these disposal options, obviously. So that's something to think about. There's challenges with that in terms of you can get some buildup depending on you can get some biochemical, you can get some reactions, redox reactions, so you can get some scaling depending on the circumstance. Again, it depends on the circumstances of the facility. So you might get scaling, you may not get too much scaling. So that's something to think about in terms of a long-term solution. And disposal by percolation, again, it goes to what we call the non-15 program. Still not very fond of that term, but it's basically the waste discharge to land option, where you have a permit and that's regulated, and you discharge to land under a permit issued by the Regional Water Board. And then usually, for cost's sake, again, for hauling, they're constructed at the site of waste generation. Doesn't have to be that way, but that's typically the requirement. And then it requires compliance with the anti-degradation policy and the basin plan, for each region, depending on what your region. Again, I'm Region 5, but there's many other regions, so you'll have to look and comply with the basin plan. And again, there's pros and cons with this option, because it may be permissible depending on the volume, character, and underlying groundwater quality. And also, sometimes there are dilution effects that can help, or evaporation, which can hurt the end result. If you have a lot of evaporation, then that's going to end up concentrating the salts again. But if you have a lot of dilution, if it's an agronomic application, then that might have the opposite effect. Then there's, of course, reuse potentially of the wastewater and maybe even the solids. They can go to land or surface water. If there's issues with that, you have to have a permit for the reuse. And then again, we have to comply with the anti-degradation policy and the Regional Board Basin Plan, which are different, but they're not. There's quite a few similarities. So that's something to think about. And then the volume, the character, and the underlying groundwater qualities are all factors in this case, because we're talking about infiltration as opposed to a lined facility. This may work well for some brines. This may not even pass the LAF test for others. So again, it's part of the potpourri of options. Brines containing primarily nitrate, you might be able to use as fertilizer. They do that in the dairy program. If it's an agronomic use, again, it looks at what are the other constituents involved. Probably not, again, feasible for high TDS brine waste. And I've already kind of alluded to this. The permitting requirements, they're regulated by the state, because we have a lot of policies at the state level, the State Water Board, and then, of course, the regional water boards, where you'd have to get a permit. The permit's in order. And there's also conditional waivers that may be applicable. But again, either the WDRs, the permits, or the waivers still must meet the water board's policies and regulations. If the state and regional board do not issue a permit, then there's the potential for non-compliance. Some drinking water systems may not produce an effluent discharge to either a sewer system or receiving water, and are therefore not regulated by the water board. In this case, it is uncertain if the concentrated brine waste or byproduct is being tracked to determine the ultimate disposal method or location. That's not unique to the drinking water brine waste. There's a lot of other industries where we have to keep a handle on where it's going and where it's being discharged. There is a need for regulatory agencies to collaborate to assure that the concentrated waste or byproduct complies with the applicable disposal regulatory requirements and is tracked to determine the ultimate fate and amounts of waste. I wanted to leave some time for questions, and I think that my previous speaker addressed some things that I was going to talk about, so that shortens this up a bit. But basically, disposal of brines is a challenge. It's not an insurmountable challenge. It's a challenge with a range of possibilities and a range of things that are easy and things that are not so easy and expensive or cheap. And you'll hear more about the various treatment options, but from the disposal options, the treatment options, there's always going to be, well, I presume there's usually going to be some kind of a brine. And so that's something to consider in the equation when you're looking at the overall cost and the overall efficacy of whatever path you take. And of course, disposal options of waste must be applicable, comply with applicable regulations and requirements, which they will. That's what our job is. But I think it's just good to look at these things holistically when we're talking about the disposal of brine waste. And I wanted to leave some time for some questions.
Rob, I have one from the web. Bruce Henningsgaard said, I don't understand the brine line. Did you say it is a pipeline that takes it to a location for additional treatment? If so, what is done with the waste stream from this treatment facility?
Okay, well, I'm not an expert on the brine line, but my understanding is that there's treatment prior to discharge to the ocean. To what degree, I can have someone else that's familiar from that region talk about it, but that's my understanding. It has to meet all the requirements, just like all other permits. And then the Santa Ana treatment process, there's treatment requirements. There's probably initial treatment requirements, and then there's treatment requirements prior to discharge to the ocean, just like we have MPDS discharges for discharges other surface water.
Okay, other audience questions? Okay, got one at the back.
Yeah, Chad Seidel, just want to ask if you can provide some context for the proportion of use of those different options. You had a great list of the potpourri of options. Could you give some context for which of them are used and to what extent?
Well, first I'd like to thank you by having that slide so I could shorten my presentation. I don't have anything quantifiable to give you, but the range of options, I don't, and anyone can speak up because no one's an expert on everything, but my understanding is deep well injection is not something that's implemented very much now. It is for other industries in the oil and gas, so it is something to think about long term. The Title 27 is pretty common. Again, there's the hauling costs and the management. That can be quite effective if, depending on how far away you are and the amount of waste. I think a big part of this is the amount of waste. And then, of course, there's the MPDS discharge, where that has its the positive sides of that is that it's a collection system, so it's already kind of built in as a collection system. And then, of course, there's the brine line. Brine line works there. There's my understanding that for Santa Ana region, there's some clear reasons why it is so effective there. Doesn't mean it can't be effective other areas, but there's a lot of other things to think about. Again, you have to think holistically of what you're trying to accomplish. So I don't know how much the quantity going into that Santa Ana brine line. And then there's the the small point of use some of that. I mean, you could look at that in the sense that if it's the net effect is no different, if they're treating it at the faucet, and that's water that was in their raw water that was provided to them at the same location. If that goes into the sewer system, if it's allowed in the sewer system, there may not be any net increase. I mean, it'd be nice if we could have that disposed of somewhere else, because that'd be a mass reduction in the salts going to that location. But that's something to think about. And then the septic system policy is something that is new, which is great. But there'll be management plans at a lot of these counties will have management plans. And hopefully they'll address issues like this in their septic system management plan.
Yoram Cohen, UCLA. I have right here.
Oh.
A quick question. You talked about the brine line, and that brine line is used primarily in the area of desalting. So if one was to apply that to areas that have nitrates, that brine line would contain nitrates. So the question is, from a regulatory viewpoint, what are the restrictions if there are currently, or is it something that is being contemplated in terms of the ability to actually discharge to wherever, whether it's to the ocean or elsewhere,
So you're talking like a
brine
brine line for,
that
for
will contain
nitrates, so to speak?
because we're talking about disposal in general here, right?
Yeah, I mean, I can answer that generally. You know, we'd have to go through the permitting process and look at the anterdegradation issues and the net effects. Certainly that's a possibility, but there's a lot of challenges with that, just like there are with the brine line. The devil's, again, in the details in terms of what pre-treatment and post-treatment, and the costs, of course, are always a factor in this. So though nothing I don't think is eliminated, but as you start looking into the details, some things become more feasible and some things are not.
Okay, I have a question from the web. Are there any WDRs for evaporation ponds for nitrate treatment? What was the daily waste flow, capital cost, permit cost, and operation cost? From Paul Richter.
Should I try to be creative and make something up? No, I can't adjust the specifics. Again, this presentation was, I realized this when I went into this, because I work with a lot of other programs, the dairies, the Title 27, landfills, you know, sewer treatment plants. That, again, this is for the disposal of brine associated with the treatment of drinking water. Again, it's a salty or nitrate-laden waste. So I can't answer this question specifically, but
that's fine. So perhaps the gentleman on the web, if you could send in a note with your contact information, we'll get back to you.
Okay.
And yeah, perfect. And we're running a little behind, so thank you, Rob. So next up, we're going to talk about a general overview of biological treatment. For that, from CDPH, Eugene Young.
Thank you very much. Good morning, everyone. I'm Eugene Leung. I'm with the Department of Public Health Drinking Water Program. I'm the water treatment technical specialist for the program. And my goal of this presentation is to give everybody an overview of the biological treatment for nitrate removal in drinking water, the basic requirements that we have set forth for vendors that have provided that type of treatment, that have gone through pilot testing and have received acceptance by the Department of Public Health, so that they can actually go to different water system and do additional testing and pilot and make a proposal for the use of biological treatment for nitrate. So my outline is I'm going to give a little bit of background, just to give a treatment acceptance timeline. We have been working with biological treatment for over 10 years. So we'll give you a little bit of timeline of where we are, just to clarify some of the treatment performance requirements, because there are some specifics that we require system that following biological treatment, they need to do some filtration and disinfection to make sure the water is safe to drink. To give some general overview of what's the demonstration, what we are looking for so the demonstration study approach. And for technologies that have been completed demonstration, what is the process after that? So I'll be giving an overview of that. Give you an example of what a conditional acceptance letter look like, and probably the key is what are the conditions that's specified in it. I'll touch on a little bit on the full-scale implementation, and if time permits, we'll touch on that. We have been working with the Central Valley Regional Water Quality Control Board to set up some demonstration projects for the use of biological treatment that we may be able to touch on. So again, this is our options chart that we have been seeing multiple times now. So you can see for biological treatment, it is in the right-hand side. It is where for nitrate reduction. As you have heard on the previous presentation, one of the key challenges for nitrate treatment is not the treatment technology itself, but it's the residual management and disposal that was highlighted in the previous presentation. So for biological treatment, is uniquely is actually to have ability to reduce nitrate to nitrogen gas, so it's discharged into the atmosphere, and then hopefully the volume of residuals that you need to handle is substantially smaller and easier to handle. So the fundamental process for biological treatment, it's instead of that one big box that you have water treatment, these are the steps that it needs to go through. So you have raw water coming in that have nitrate over the drinking water standard. The first step, you need to go through some pretreatment. You need to put in some chemicals that you need to put in is actually to provide electron donor. And then for certain waters, you need to put in some nutrients for it to work as well. So there's a nutrient addition. The electron donor could be coming in the form of hydrogen gas, or the other ones that can come in will be acetic acid, so simple vinegar that you need to go in. So you go through a biological reactor where the oxygen is first consumed, and then it's left with an anoxic condition or lack of oxygen. From there, the nitrate is broken down ultimately to nitrogen gas. And the steps that goes through is highlighted in the bottom, where you have nitrate going into nitrite and eventually to nitrogen gas. Following the biological treatment, because you've now taken out all the oxygen from the water, you need sufficient post-treatment, which includes first, you need to re-aerate, most likely, to bring oxygen back into the water. If you're treating all of the water, if you're treating only part of the water, maybe 50% of it, and then you can blend back, that could solve part of the problem. In addition to that, because the biological treatment, you have biomass that's built up, that's done the work. So you need to go through a filtration process to remove the biomass. To do that is pretty much like surface water treatment rule, where you need to put in a coagulant to help you pick all the biomass together so that you can filter it out efficiently with different types of filters. We can have sand filters or membrane filters, whatnot, but you need to remove the biomass. And following that, you need to put in disinfection. So chlorine is the most typical one for groundwater system because they usually don't have a disinfection byproduct problem. So you use some chlorine to disinfect it so that you can inactivate any pass-through biological bacteria that may have passed through the system. You disinfect it before it goes into the distribution system and where you have the treated water. So technology variations. So what you saw on the previous slide is the basic steps. So the key design differences that we have seen from the different vendors that we'll be presenting this afternoon is the design of the bioreactor. We have a system that has a fixed bed design. What that means that the growth media for the bacteria is actually just a fixed sand filter or a GAC filter where the water flows downward through the filter media and the bacteria will grow on the media itself. Another design that we have is a fluidized bed. This one is the water flows upflow so that the media is actually partially fluidized, and then you have your bacteria growing on the media itself. We have a couple other ones. There's a membrane biofilm reactor. The best way I can describe is a kind of rolled up membrane. It's where the biofilm will be growing on the membrane surface itself, and the water passes through along the surface of the membrane. That's where it gets reduced from nitrate to nitrogen gas. There are also proposals for using a continuous stir tank reactor design, or a CSTR, where you allow a growth media that's continuously circulating in a bioreactor. And the growth media is, I would describe them as maybe crouton-sized little sponges that's being mixed inside the bioreactor. And last but not least, which is different from all of the above, is a Biocatalyst, which is from the company MicroV. They have bacteria that is actually pre-populated inside capsules. So instead of using bacteria that's naturally occurring in the groundwater, they come pre-shipped with bacteria that's ready to break down the nitrate to nitrogen gas. So far, there is very commonly used in wastewater treatment, but we don't have any for drinking water treatment so far, which is using membrane bioreactor. That's for reduction using regular submersible filtration membranes and allow the biological treatment to occur. We haven't seen that yet. So as mentioned earlier, the electron donor use is typically hydrogen gas. Sometimes we have looked at ethanol as well as acetic acid. For the nutrient, some waters may not require it, but if you do, it will be phosphorus-based. So here's some pictures to show you what it looks like for the bioreactors. On the left is the Envirogen fluidized bed design. This is actually a full-scale treatment plant that is completed construction and is in the process of starting up. It's located in West Valley Water District down in Southern California in San Bernardino County. And this is actually a 2,000 gallons per minute treatment plant, and it is in the process of being startup, and so that will be the first in the state for us for use for drinking water treatment will be this particular one that is full-scale permanent one. The other ones on the right that you see, these are the pilot units that we have. One is from WQTS, and the other one is from Carollo. And they emphasize on the different bioreactor design. So the fluidized bed process, as I've explained earlier, you have raw water coming in, where you put in the nutrient and electron donor, and then it goes through the upflow process for the fluidized bed reactor, and this is the diagram to help explain that. And then we have the fixed bed processes, which is just comes up from, you have groundwater coming up, you put in your acetic acid and your phosphoric acid, it goes through the bioreactor process. One of the co-contaminant that could be taken out from biological treatment is in addition to nitrate removal, is also very efficient for perchlorate removal. For a water system that needs to deal with both nitrate and perchlorate, this is a possible solution for it. But in order for it to work, it needs to first remove all the nitrate before the perchlorate removal will start to occur. Following that, they put in a polymer to use as the coagulant aid, and then they need to degas to release all the nitrogen bubbles that have been formed from the biological process. Following that, you have a polishing filter to remove any turbidity and biomass that have been created, and then you have chlorine for disinfection before it goes into the system. For a membrane biofilm reactor, this is the aeronite technology. This is the one that I've talked about that is a rolled up membrane where they have, they use membrane to deliver the hydrogen and CO2 to the actual biomass that's growing on the surface of the membrane. And then water passing by it will contain nitrate, and the biomass will consume the nitrate and reduce it to nitrogen gas. And this is the Biocatalyst from MicroV. This is the one that comes pre-populated with a bacteria that is inside these capsules where the water can come in, go through this bioreactor, and it can effectively break it down to nitrogen gas. Some of these technologies that I've covered have received conditional acceptance from department, and some of them are in the process. And this one is for the continuous stir tank reactor, or CSTR. It's by MIH Water. This is the one that they have the water coming in, going through the bioreactor where they have the sponge, the little sponges, crouton-sized sponges, mixing in the bioreactor for the reduction of nitrate. So the microbes at work, in general, for 5 of the 6 products, we use the general requirements that they use indigenous microorganism that is already in the ground. So there's no seeding of microorganisms. You just remove so during the startup process, all you do is just remove the oxygen so that the nitrate breakdown starts to work. So there's no seeding, and then you will see the nitrate reduction start to occur. If you allow the process, or you give them enough electron donor and you have a source of perchlorate, it will actually start removing perchlorate. And if you have removed all the nitrate and perchlorate, you could go to the level that we don't want. It will start breaking down sulfates. Then you break that, you end up having hydrogen sulfide problems. So we don't want to go that far. But in general, for today's presentation, we generally concentrate on the nitrate reduction part of the process. So the current status that we have 6 companies that have either in the process of completed the conditional acceptance by our program. So there are 4 of them that have received the conditional acceptance letter, and they're listed on this slide. Most of them have, there's only one system right now with a full-scale plant. That's the one at West Valley Water District that I mentioned earlier, with 2,000 gallons per minute in San Bernardino. Then on all the other projects, the water systems is in the process of deciding whether they want to proceed with biological treatment, or they're evaluating one of the other existing treatment technology. For 2 more water systems, for 2 more vendors, for the CSTR for the Hall reactor by MIH Water, and for the Biocatalyst, one has just recently completed the challenge testing at West Valley Water District, and then another one is about to start this month at the Sunny Slope Water Company down in Los Angeles. So we'll have more data to share to see how the overall process works. Conditional acceptance letters, these are examples of all the conditions that we have given. One of the key things that we want to highlight is that for most of these treatment technologies, we only have demonstrated them to operate on a steady state process. that as a biological activity, it takes time for us to come up to speed. It can take days to weeks for it to come to a steady state. And once it's running, generally our goal is to keep it running all the time so that you have a steady process. You will be feeding chemicals on a constant rate so that because the influent concentration will be pretty steady and you'll have a good quality, consistent treated product. So that's one of the key requirements is steady state. And then following it, originally we were in the original acceptance letters, we actually required full surface water treatment rule following biological treatment, but we have reduced it substantially now to just for a system that they need to provide low turbidity water through filtration, but they're not subject to the requirements of surface water treatment rule, and then they just require that they disinfect the water to meet 4-log virus CT. What that means in plain language is that we reduce a much shorter disinfection time compared to what we originally required under surface water treatment rule. So the highlights of the treatment performance is that there's a 4-log virus disinfection required. The treated water after it comes out of the system needs to be coliform free. You have to keep in mind for drinking water, they need to meet all drinking water standards. It's not that we can just solve the nitrate problem. We end up having other treatment drinking water issues downstream of it. So we need to look at it as a big picture holistically. One of the things that we require is that for the hydrotrophic plate count, for the treated water needs to be less than 500 CFU per milliliter. The turbidity coming out of it will need to be low. We set it at 0.3 NTU because that will really tell us that there's filtration going on, because the groundwater coming in is actually really low turbidity already. And sometimes even if you put in a polymer, you need to put in and give it enough energy, mixing energy for it to work well so that you can have the low turbidity achieved consistently. The corrosivity of the water must be monitored and controlled because we don't want to solve a nitrate problem and cause a lead and copper rule problem downstream, that you have water the water is corrosive and then you have having a lead problem. Disinfection byproduct is a concern. We require them to monitor according to the disinfection byproduct rule. But so far, most of the system that we have tested, there's not a disinfection byproduct that we have seen, a problem that we have seen. The water must be aerated after biological treatment because we've taken out the oxygen, as I mentioned earlier. If we're just doing partial stream treatment, maybe apply blending and aeration can restore the water to the sufficient level for dissolved oxygen. And finally, the key thing is the water quality. It must meet all secondary drinking water standards. What it means to you and me is that the water looks good and tastes good, that someone will want to drink it after all this treatment. The chlorine residual and turbidity monitor is, for the large systems, we require them to be monitored continuously so that we know that it's working really well. For the coliform and HPC, it must be monitored by either weekly or monthly based on the system size. And then for pH, we allow daily grab samples. So for pilot testing, these are the key phases of biological treatment coming online. First phase, you need to figure out how long does it take the system to get acclimated, because you need to do something with that water when it's not meeting the standard. So biological acclimation is important. Phase 2 is how do you figure out your optimization. You have a theoretical dose of how much of the electron donor you need to move in. So once you get to this phase, you figure out what dose is needed at your specific site. And then once you get it into cruising altitude, you have your sustained removal, so the system is working pretty well. And then last but not least, we go through robustness testing. So we go through different phases of purposely cutting off chemicals and see how quickly does the system fail. And then we restore the chemical to see how quickly it bounces back. This is very critical for us, especially for small water system. We need to know that since someone cannot be watching this over all the time, we need to see how critical these parameters are. If they are critical, we need them to put in sensors ahead of time, maybe flow sensors for the chemicals. If they do detect a chemical feed failure, you'll sound an alarm and shut off the system before it starts producing water that doesn't meet nitrate standard and going into the system. So I think we're running out of time, so I'll go a little bit quick. For the general demonstration approach, as I mentioned earlier, you would go through the startup procedure to just make sure how it's being ramped up. Once we get to steady state operation, we allow the system to be optimized at just a flow rate chemical dose. We go through systematically test for chemical interruptions, water flow interruptions. As with anything, the well will break down. So once you break down, how do you bring it back up after you fix the system intentionally? Can it survive hours or days with no water flowing, and when you turn it back up, will it work properly? So we need to take a look at system recovery. How well does the system recover? We are looking at site site-specific testing is required because different water conditions may not make it feasible for biological treatment. So there's some site-specific testing that's required. So overall, the key concerns that we have is during the startup or a system upset, and can the water be discharged? Like for systems here, that it may take weeks for us to come up to speed. What do we do with those water that's off spec or not meeting standard? And then what would be the source water for the drinking during the system upset? Do we need to provide a large storage tank so that we can anticipate these things are going to happen? Because what we don't want is the system fail. You have water that exceeds the nitrate get into the system. You end up needs to be flushing all the water out of the system to restore water service. So maybe we need to include storage tank as part of the design. So here's a picture of the reliability features. The take-home message is we need a lot of online instruments to keep an eye on to make sure that there's sufficient oxygen removed, sufficient oxygen put back into the system, that the nitrate coming off of the system is consistently meeting the standard, and that you're reliably disinfecting with a chlorine residual analyzer. And any questions, please do let me know. I do have phone number and email contact, and emailing me the questions will be best. Thank you.
Okay, well,
Thank you. This is very interesting. I had one question about, or you mentioned there is no membrane bioreactors currently being used for this. Can you tell us the main obstacles for that?
There really isn't an obstacle. Is all for California for drinking water treatment. We require conditional acceptance. So for a membrane bioreactor, for them to approach us, we'll need the vendor to partner with a drinking water company, a public water system, and say that we would like to perform a pilot scale demonstration to show that our membrane bioreactor will work. So then they will go through the steps that I've outlined here to demonstrate that the system will work and have some robustness testing, provide us the data to show that the key thing is that the vendor has control over the biological process that's operating optimally in a steady state process, and that so with all the information that's provided through a pilot study or demonstration study, we can issue them with a conditional acceptance letter. So with the conditional acceptance, it means that they have demonstrated they can control the treatment technology, and then at all the future sites that they propose to use the technology, they will do probably a pilot study, but probably not as extensive as the one that's included for the original conditional acceptance. And then they can go around the state or any particular water system that will be interested in using technology. So the conditional acceptance is the pre-screening to make sure that it works well and that they have control over it. And then they go through site-specific additional pilot testing, and they will work with our field offices to ultimately to do the permitting for each location. So so all of that is through the drinking water treatment side. So as mentioned, there are some residuals problem. There's off-spec water that they need to work with the local regional board, and there are some disposal maybe of the sludge that they need to work with them as well to make sure that everything is properly disposed of.
there's one at the back. And if I could ask you, if you're asking a question, if you could identify yourself, please, for those on the web. Thank you.
Kim McFarland with Gallo Family Wineries. I noticed that you mentioned ethanol, acetic acid, and hydrogen gas as the electron donors. Are you planning on looking at any other substrates that will be approved by the CDPH?
For CDPH, any electron donor, the prerequisite is that it is NSF, NCNSF 60 certified as a drinking water additive. So as part of the pilot process, it could be demonstrated that you can use a specific electron donor and that is certified as a drinking water additive, then it can be used. So far the ones that we have used is generally acetic acid and hydrogen gas. Thank you.
Any last questions before lunch? No pressure. Okay. We've cut into our lunch a little bit, but if I could ask all of you to be back here around 1 o'clock, we'll start promptly at 1:05. Thank you.